I hope you actually did pause this before you tried this. I hope also that you tried all four, because this is actually symmetrical about the x-axis, the y-axis, the origin, and the equation y equals x. It's symmetrical to all four. And let's talk about y. Okay, the y makes these problems make a lot of sense. Hopefully, we're going back to number 1 now for a second. You notice that this is a quadratic that is translated up 3 units. So it should look something like this. Pardon my ugly drawing. Now you can pretty much notice that it is not symmetrical about that x-axis. It's not reflected over the x-axis, but it is foldable or symmetrical about the y-axis. It's not symmetrical about the origin here because you can't rotate it around. And it's not symmetrical about the line y equals x. So that makes a lot of sense to us when we talk about what the symmetry means. The second equation you might not recognize right away, but if you were to graph this, it's actually a circle. That was actually a pretty good circle. Good job, me. And this is symmetrical or foldable about the x-axis, the y-axis, the origin, and the line y equals x. It's symmetrical in all those ways because it's a perfect circle centered at the origin, which is pretty cool. Okay, away from the pretty cool stuff, we're going to pop back down for some more vocabulary. The last 2 pieces of vocabulary that we're going to be talking about for a lot of these functions is one-to-one functions and end behavior. A one-to-one function is a function that passes both the vertical line test, which you've heard of before, you know, crosses a vertical line more than once, it's not a function, and actually the horizontal line test, which is exactly as it sounds. You do a horizontal line test, and it has the same requirements as the vertical line test. Basically, a one-to-one function means that there is only one y for every x and one x for every y. None of the x's and none of the y's repeat. That's a one-to-one function. End behavior we have talked about. It's what happens to the y values at the ends of the graphs. Okay, we're going to talk about these end behaviors in 2 limit statements. We need to write a limit statement for the left side and the right side. So as numbers go to negative infinity and infinity, what happens to those endpoints? The way that we write these limit statements, remember, is the limit as x approaches some number. And we're going to do this in 2 ways. So we're going to start off first with negative infinity of the function f of x. We'll name these all f. Goes which direction? Where is this arrow headed? Downwards, so we'd say the limit as x approaches negative infinity for f of x is negative infinity. And just the opposite, the limit as x approaches positive infinity, so as it goes to the right, is positive infinity because this arrow is going up towards infinity and it's going to keep going forever. Okay, end behavior. If we look at the end behavior of this graph, we've got to be able to talk about what happens on the left side and on the right side. As the x values go to negative infinity and infinity, where are the arrows going? Where are the y values going? So the limit as x approaches negative infinity of f of x. So let's look at the left side, the negative infinity side. This is an exponential function. And a property of exponential functions is that it has a horizontal asymptote here at 0 that this line will get very, very close to but never cross. So this function itself has a limit as x approaches negative infinity of 0. That's its end behavior. It's never gonna reach, it's gonna approach, but it's never gonna quite reach 0. And as it goes the other direction to the right, we can see the arrows going up towards infinity. So its end behavior on the right-hand side, as x approaches positive infinity, is infinity. Okay, the limit statements are really not that complicated. Saying them out loud, you might get tongue-tied, but you really do just put limit, Lim, x approaches infinity of the function is whatever the limit is. Okay, so here's where the video gets really long. We're about to start going through all 12 of the basic functions. Definitions are done, so if you're just here for definitions, you can pause the video and be done. But we're going to go through each and every one of these 12 basic functions, going over these properties. And I'm going to go through them kind of fast because it's just information at this point. The first of the 12 basic functions is the linear function, sometimes called the identity function. Its equation is y equals x. And so since the input equals the output, you can plot the points -2, -2, -1, -1, 0, 0, 1, 1, and 2, 2. That's my parent function for linear. Its domain is unbounded, so it goes from negative infinity to positive infinity. Its range also goes from negative infinity to positive infinity. This is symmetrical about the origin, which again, remember, means that this is an odd function. This function is not bounded, doesn't have a lowest or highest point. It does not have a vertical or horizontal asymptote. It is continuous, so we don't have any discontinuities. It's increasing on its entire domain, again, remember, increasing intervals, we're reading the graph. Don't follow this arrow. Read the graph. We're always going uphill, so it's increasing the entire way. There's never a point that we're decreasing. It does not have any extrema because it doesn't have a maximum or minimum point. And the way that we would write its end behavior in two limit statements is the limit as x approaches negative infinity of this function is equal to negative infinity, since that arrow is headed downwards. Its end behavior is negative infinity. And the limit as x approaches positive infinity for this function, since that right-hand side is going up, is going to be infinity. These are the properties that we're going to name for all of the 12 parent functions. So again, this is going to get a little repetitive, but it's pretty cool when you start seeing all the things you actually do know about these functions right away. The quadratic function is our next parent function. This is sometimes called the squaring function. It's called that because its equation is y equals x squared. So we're squaring our x values to get our y values. A quadratic, so we have the input of 0, 0 squared is 0, 1 squared is 1, 2 squared is 4, -1 squared is 1, and -2 squared is 4. Again, please don't judge my parabola. Oh, that was pretty good, actually. That's the quadratic parent function. Its domain, again, for this parent function, is from negative infinity to infinity. There's no point that this is going to stop on its domain, but since it has a lowest value, its range is from 0 to infinity, because that's as low as it goes. And I used a bracket because this point 0, 0 exists, like it's on the line, on the curve, so we know it's a part of my range. This is symmetrical about the y-axis. It's foldable on the y-axis, which remember makes it an even function. Since it has a lowest value on its range, we can say it's bounded below, but it does not have any asymptotes or discontinuities. It's increasing from 0 to infinity and decreasing from negative infinity to 0. Right, increasing over here and decreasing over here. Not following the arrows, but reading it from left to right. It does have an extrema though, so it has an absolute minimum at 0, 0. And our end behavior is the limit as x approaches negative infinity for this function. So on the left-hand side, this arrow is going up. So its end behavior is positive infinity. And the limit as x approaches positive infinity of this function f of x, since that arrow is going uphill, is also infinity. Our next function we're going to talk about is the cubic function. The cubing function is sometimes what you see, but it is a cubic function. It's called a cubic function because its parent function is y equals x cubed. If we plug in some points, 0 times 0 times 0 is 0. 1 times 1 and 1, whoa, said that wrong. 1 times 1 times 1 is 1. And negative 1 times negative 1 times negative 1 is negative 1. So our cubic function looks something like that. That was not too bad either. Its domain is from negative infinity to infinity. Its range is also from negative infinity to infinity, since both those arrows go off in both directions. This is symmetrical about the origin, just like linear was, which means that it is odd. It is unbounded. It does not have any asymptotes or discontinuities. And it is actually increasing on its entire domain, which again throws people off. Remember, you're not following the arrows. You're reading the graph from the left to the right. As I'm going to the right, this entire cubic function increases. The parent function of a cubic does not have any extrema. Although some cubic functions do, the parent function does not have a maximum or minimum. And its end behavior, the limit as x approaches negative infinity for f of x, is equal to negative infinity. And the limit as x approaches positive infinity for this function is positive infinity. That's the direction in which the arrows are headed at the end of the graph. The next basic function that we have is called the reciprocal function. I will sometimes, most of the time, refer to this as the rational function, because that's my habit. And it's called that because it's a rational function. It's a fraction, or a reciprocal. They're reciprocals of each other there, y and x. So we're going to graph this function. We're going to label 2 points, and you're going to find that it has a horizontal asymptote and a vertical asymptote. 2 things we know. If we plugged in 1, okay, so 1 over 1 is 1. If we plugged in negative 1, 1 over negative 1 is negative 1. But if I plugged in 0, hopefully your spidey sensors are telling you we would have a vertical asymptote right there, because you can't divide by 0. Okay. Also, since this is a rational function, this is bigger on bottom. This is a Bobo. Bigger on bottom. So we would also have a horizontal asymptote at 0. Thanks, Bobo. Which means our rational function, or our reciprocal function, is going to look a little something like this. Not my best, but not my worst. Okay. Ooh, this one's funky. You gotta love it. Okay, so since we know this has a moment where the graph does not exist at that 0, our domain is not all real numbers. Our domain is negative infinity to that point 0, pick it back up after 0, and keep going to infinity. It just can't be 0. And if you look at our range, it's kind of the same. The bottom goes to negative infinity, and then we have a hole at 0, our horizontal asymptote. Pick it back up right after 0, and go to infinity. This function has 2 symmetries. It is symmetrical about the origin, because if I took it and rotated it, it would land right on top of itself, which means it's odd. And it's actually symmetrical about that line y equals x. Okay, it's that diagonal line. It is not a bounded function. It does have asymptotes though. So remember, our vertical asymptote is that line x equals 0. That makes the denominator 0. And our horizontal asymptote, this is also 0 because of Bobo. Thanks, Bobo. It does have a discontinuity. Remember, we had to pick up our pencil. Its discontinuity appears at y or x equals 0 because of that vertical asymptote. It is a non-removable. You couldn't plug that with a pencil. You'll also hear this called an infinite discontinuity. But we were using the word non-removable. Now this tricks people up. This is actually never increasing. This is increasing on its entire domain, decreasing on its entire domain from negative infinity to 0, back up at 0, and to infinity. And let me show you why. This is going down. That's pretty obvious, right? But if we read the graph from left to right, isn't this also going down? Don't follow the arrows. Actually look at the graph from left to right. This has no maximum or minimum value because there's no maxes or mins. And our end behavior is the limit as x approaches negative infinity for the function, our horizontal asymptote 0, and the limit as x approaches positive infinity of f of x, again, thanks Bobo, is 0. Our fifth parent function, our fifth basic function, is the square root function. We've seen this guy a lot today because he was our example for all our symmetries. So the square root function, parent function equation here is y equals square root of x. Let's label 3 points. Now this one I'm actually going to set up a table of x and y values to make it easier on myself. Let's do the square root of -1. Oh wait, we can't do that. It would be an imaginary number. So we're going to say, never mind, we're going to go to 0. The square root of 0 is 0. Square root of 1 is 1. Square root of 2 is some irrational number, so is 3. If I take the square root of 4, I'm going to get 2. So that gives me 3 points to plot, 0, 0, 1, 1, and 4, 2. There's my square root function. That's what the whole thing. This one's pretty cool because its domain is very interesting. It starts at 0 because we can't take the square root of a negative number, which means its range also starts at 0 and goes to infinity. Pretty cool. Since we use this to explore symmetry, you'll realize it's not symmetrical at all. None. Not symmetrical at all. It is bounded below because there's a lowest value. It does not have an asymptote or a discontinuity. And this is increasing on its entire domain from 0 to infinity and not decreasing. It has an absolute minimum. And that absolute minimum is 0, 0. It will never be a negative y value because you can't take the square root of a number and get a negative number. It just doesn't work. Our end behavior is very, very interesting here. Don't try to get ahead of me. And I'm actually going to do these out of order. So I'm going to do the limit on the positive side to positive infinity first because that part's easy. It's going to infinity. Piece of cake. The end behavior for this one, on the negative infinity side, you don't actually write negative infinity because it's not going to negative infinity. It goes all the way, it approaches 0. Doesn't approach anything else because that's the beginning of my domain. And we can only approach 0 from the positive side. Here's what I mean. Here's 0. This is the negative side of 0, and this is the positive side of 0. A limit means we're getting closer and closer to that number. So as we get closer and closer to 0, only coming from this positive side, we can talk about its limit. We can't say anything for this side because it doesn't exist over there. So we actually use this notation to show that we're going towards 0, but only from the positive side. Interesting little piece of calculus there for you. But the limit as x approaches 0 from the positive side of f of x is equal to 0. Super interesting stuff right now. The sixth parent function, we're halfway there. Hang on with me, guys. Is the exponential function. There are many parent functions. Again, I'm using air quotes, you can't see me. But the exponential function we're going to play with today is e to the x. It is pretty much the basic exponential function. Again, we'll make a table of x and y values to help us out. If we plug in 0, we would get e to the 0 power, which is 1. Anything to the 0 power is 1. And if we plug in 1, we're going to get e. And if you don't remember, e is approximately 2.718. So we can kind of graph that a little bit for ourselves. We have 0, 1 and 1, 2.7. And we'll be able to graph this exponential function. Hopefully you remember this from Algebra 1 or something like that. We also have a horizontal asymptote here at 0. we will never touch 0 for an exponential function, which is going to be super interesting for us. The domain of this function, again, is all real numbers because there's nothing that's going to make it mess up on its domain. But since it has that lowest value of 0, but not including 0, I would use the parentheses here, 0 to infinity. This has no source of symmetry. It is bounded below because we have that lowest value, and it has a horizontal asymptote at the line y equals 0. Doesn't have any discontinuities, so we'll put NA for that. It's increasing on its entire domain. Does not have any extrema, no maxes or mins. And its end behavior, the limit as x approaches negative infinity for this function is headed towards the number 0. And the limit as x approaches positive infinity for this function is infinity, because that arrow is headed upwards as we go out to the right towards positive infinity. Our seventh parent function, our seventh basic function here is the logarithm function. We're getting into, again, I'm using air quotes, basic functions that you may not be as familiar with what their basicness is. But the logarithm function has plenty of types. The one that we're going to use is the natural logarithm. So y equals the natural log of x. That's the one we're going to be talking about. That's ln for natural log. Okay, let's set up a table of values again, because this is not a common one. Again, if we plug in 1, we're taking the natural log of 1, which is 0. And we're actually going to plug in e this time, because the natural log of e is 1. And you can test that in your calculator again. But this gives us 2 points to plot. We have the point 1, 0, and e, 1, which remember e is about 2.71. It's pretty good to graph. So this is what your logarithmic function might look like. I don't know if you can hear that. My dog is drinking water. I apologize. We have a vertical asymptote here. A vertical asymptote, because that graph is never going to touch the y value of 0. This one's domain is only from 0 to infinity, but not including 0 since we have that asymptote. But its range, interesting enough, because that arrow goes all the way down, is from negative infinity to positive infinity. Wild. Super cool stuff. This has no sorts of symmetry. It is not bounded because we're talking about bottoms and tops, highest and lowest points. Sorry. It does have a vertical asymptote at x equals 0 because you can't plug in 0 to the natural log. It doesn't work. But it does not have any discontinuities. It's increasing on its entire domain from 0 to infinity. Never is it decreasing because, again, it's always going up. It does not have any extrema. Its limit statement is also going to be kind of interesting for end behavior because similar to the square root function, x on this side, on the negative side, can only actually approach 0 from the positive value. But the limit as x approaches that 0 from the positive side is actually negative infinity. And let's talk about that. So we can only go the furthest to the left all the way to 0, and it's only going to approach 0 from the positive side. It's going to get closer and closer but never touch, and that graph is going to keep going down to negative infinity. Such interesting stuff. The limit as x approaches positive infinity for this is also positive infinity, so it can keep going up pretty slowly. The eighth parent function or simple equation, basic function that we're talking about is the absolute value function. You should see this one and be pretty familiar with it. You used it in Algebra 2. This is y equal to the absolute value of x. Hopefully you remember how to plot this one. The absolute value of 0 is 0, of 1 is 1, of 2 is 2, of negative 1 is 1, and of negative 2 is 2. So this is our absolute value function. Its domain is all real numbers, so from negative infinity to infinity. Its range, though, it does have a bottom, so it's from 0 to infinity. This one is symmetrical about the y-axis, which means that it's even. It is bounded below. It does not have any asymptotes or discontinuities. And it's increasing on the right side, so it's increasing from 0 to infinity. And it's decreasing from negative infinity to 0. Again, don't follow the arrows, read it from left to right. Which means that we have an absolute minimum for our extrema, absolute minimum, at the point 0, 0. And our limit as x approaches negative infinity for this function goes up, so it's infinity. And the limit as x approaches positive infinity of f of x is also positive infinity, because both arrows at the end behavior are going up. These next two functions you might actually not be that familiar with at all. The first one is a basic function called the greatest integer function. It's called that a lot. I also call it the step function. Okay, the step function, it's called the greatest integer function. Its equation is y equals integer of x, int of x. Okay, it's called the step function. Basically what this means is every x value that you plug in, like maybe 0.7, is plotted as the next highest integer. So the next highest integer or whole number is 1. If I had like 1.5, the next highest integer would be 2. If I had 2.1, the next highest integer, not that I'm rounding, but the next highest is like 3. So what this ends up looking like, and I'm going to zoom in here because I want to make sure I get this right, is that there are a bunch of discontinuities going on because you have a coordinate point here, and all of these are the same, and then it's going to jump, and then it's going to jump, and then it's going to jump, open circle, it's going to jump, and then it's going to jump. You can kind of see what's happening here. This is why it's called the step function, because it looks like a bunch of steps, but it is called technically the greatest integer function. I like to call it the step function. That flows off my tongue better. There's our step function. So every x value is just the next largest x value. So the domain here is actually all real numbers. There's no point along the x-axis we can't include. But the range is not really quantifiable in interval notation because you'd write like a bajillion and a half intervals. So what we would say is we would just say all integers. And those of you who are going into higher level maths than this, there is actually a notation for this. You would say that x is an element of the integers, and integers is the letter capital Z that's bolded. So that's how I draw mine. You can just say all integers, and that's fine with me. But x is an element of the integers is how mathematicians would write that in higher level maths. This has no symmetry because it's all sorts of wild. It is not bounded because there's no highest or lowest point. It doesn't have any asymptotes, but it has like a million discontinuities. In fact, it has an infinite amount of discontinuities. And so you would say infinitely many at all integers. Because there's like a million breaks, right? There's infinitely many breaks in this thing. Since this is kind of weird, we actually don't really talk about increasing or decreasing for the step function. And it has an infinite amount of extrema. So again, infinitely many at all integers. But we can write its end behavior. So as this function moves to the left, as it goes towards negative infinity, this function is getting smaller and smaller, which means we're headed towards negative infinity. And the limit as x approaches positive infinity for the step function is still going up, so it's headed towards positive infinity. The last function on this page, number 10, is called the logistic function. Make sure you see that's not logarithmic, it's logistic function. This is a basic function that you really probably have never seen. It's going to be y equals 1 over 1 plus e to the negative x. Ooh, yeah, wild, right? That's called a logistic function. And this is actually really, really cool. So we're going to label 1 point and then the 2 horizontal asymptotes. So I want you right now to plug in 0 to this function. You'd get 1 over 1 plus e to the 0 power. Anything to the 0 power is 1, so this is the same thing as 1 over 2, because 1 plus 1 is 2. So we know we have a coordinate point 0, comma, a half. Now there are 2 horizontal asymptotes here. There's a horizontal asymptote here at 0. And there's going to be a horizontal asymptote here at 1. Because we never actually can, with this function, get smaller than 0 or larger than 1. So it looks a little something like that. Its domain is from negative infinity to positive infinity, but its range is only between 0 and 1 with horizontal asymptotes there, so it's never going to reach them. This function has no sorts of symmetry. It is bounded on top and bottom, so above and below. It has 2 horizontal asymptotes, one at 0 and one at 1. But it doesn't have any discontinuities. I didn't have to pick up my pen to draw that function. It is only increasing on its entire domain, so it's never decreasing. It doesn't have any maxes or mins. And its end behavior, the limit as x approaches negative infinity for this function. So as it's going towards negative infinity on the left side, it's actually headed towards 0. And the limit as x approaches positive infinity for this function is headed closer to 1. Last 2 function, guys, you're almost there. These are become more interesting and or relevant to you in the second semester, but they are the sine and cosine function. In the sine function, okay, the function equation is y equals the sine of x. Please do not say sin, okay, it's the sine of x. This function oscillates is the word we would use between -1 and 1. The sine function starts at the origin, is going to go up to some value 1. It's going to go through the origin again, or through the x-axis, down to -1, and then back. That circuit right there, for lack of a better word, that pattern is called a period. And this is going to keep going over and over again, so it looks like a squiggle. It looks like a squiggle. Its domain is from negative infinity to positive infinity, but its range is only from -1 to 1, inclusive, because we actually do touch the point of -1 and 1. The sine function is symmetrical about the origin, which you can't really tell from the picture I've drawn, but if you have a full-scale sine function, like on Desmos or something, you can imagine rotating it and it lands right back on top of itself. Since it has a maximum and a minimum, it is bounded. It does not have any asymptotes or discontinuities, though. And since it's like continually increasing and decreasing, no matter, as long as you draw it, it will be changing, increasing and decreasing. We actually don't really talk about increasing and decreasing for this one either. And since it's going to continue to go up and down like this, it's going to have an infinite many extrema. And again, because it's going to go up and down, there is no really end behavior because you just stop graphing it. It doesn't actually have a direction it's always going. It will always flip back down or flip back up. To actually get out of answering some questions about the sine function. The cosine function is related to the sine function. It's going to look pretty similar. It just changes how we started. It's actually shifted a little bit. The cosine function, which is y equals the cosine of x. Please do not say cos x. Ooh, that bugs me. Again, is going to oscillate between -1 and 1. But this time it doesn't start at the origin. It actually starts up at my value of 1, hits the origin, goes to -1, goes back through the origin, and up to my value of 1 again. So it is kind of like just a shifted version of that sine function. It's just horizontally shifted. Still going up and down across the entire thing. It has a domain of -infinity to infinity, a range still of -1 to 1. This one is symmetrical about the y-axis. If I drew it nicer, it would actually look like an even function. You could fold it along the y-axis and it would land on top of each other. Again, check Desmos for that one. Just like cosine, it is bounded. It does not have any asymptotes. It does not have any discontinuities. We're not really going to talk about increasing and decreasing. It has infinitely many extrema as well, because it is still kind of the same shape, just shifted. That's not how you spell that. And because the end behavior is always going to change depending on when you stop graphing it, we don't really talk about end behavior. And that, my friends, is the 12 basic functions. You have hung on for probably the longest lesson video I've ever put on YouTube. The last little bit is just kind of talking the way your homework will be talking. And I've given you a little cheat sheet, and I've given you this cheat sheet in large as well at the end of your notes packet. But we're going to go over this. Use the 12 basic functions to answer the following. 9 of the functions have the domain of all real numbers. Which 3 do not? Now, I don't really want you to like cross things off like I'm going to. I can erase on my iPad, so it's kind of unfair. But here we go. So let's look at the domains of all of these. So the first one, domain is all real numbers. All real numbers, all real numbers, all real numbers. Oh, that one's not. That one's not. All real numbers, all real numbers, all real numbers, all real numbers, all real numbers. So here's the few that do not. Your reciprocal, which again, I probably will call rational a bunch of times, your square root, and your natural logarithm. Those 3 do not have a domain of all real numbers because those were the 3 that we had to do something with when we were doing this algebraically to figure out the domain. We had to set the reciprocal, the denominator equal to not 0, the square root equal to larger or equal to 0, and the natural log or log greater than 0. Which functions have no negative numbers in the domain? Of these 2, which is defined at x equals 0. So we're looking at domains again for the ones that have no negative numbers. Okay, so let's look for no negative numbers in our domains. The domains are all listed. Here's something with no negative numbers in the domain. Here's another one with no negative numbers. So we're going to answer the square root and the natural logarithm. But based on these symbols, one of them is defined at 0 and one is not. Hopefully you're remembering that since the bracket means that it includes 0, your square root is defined at 0. And the natural logarithm has that vertical asymptote there, so it is not defined at x equals 0. Okay, next one. It says, which 3 functions are bounded? Let's look at the pictures here for boundedness.